I will prove the phase rule in this video. The phase rule is F equals C plus 2 minus P. F is the number of degrees of freedom or the number of independent variables that may vary freely. For example, if we have an ideal gas, PV equals nRT. Among pressure, volume, and temperature, there are only two independent variables that may vary freely. Therefore, we say there are two degrees of freedom. It can be PV or PT or TV. C is the number of chemicals in the system, and P is the number of phases. So usually we have solid, liquid, and or gas phases. Now the total number of independent variables is the number of phases times C minus 1 plus 2. This is because if we assume all C chemicals exist in each phase, and then there will be C variables in each phase. There are x1, x2, x3, all the way up to xc. They are the mole fractions of these C chemicals. But because we have an equation, the sum of those mole fractions is always equal to 1. And then we say there are only C minus 1 independent variables in each phase. Therefore, we have a total number of P times C minus 1 independent variables in the total of P phases. However, there are two other independent variables. One is pressure, one is temperature. How about volume? Again, the volume depends on pressure and temperature. It is not counted as an independent variable. So therefore, we have P times C minus 1 plus 2 independent variables. But this expression does not look even close to the phase rule. So what's going on? Remember, we assumed that all C chemicals exist in each phase. And then for each chemical, its chemical potential in phase 1 equals its chemical potential in phase 2, equals its chemical potential in phase 3, and so on. And we have P minus 1 equality for each single chemical. We have to remove this P minus 1 variables. Therefore, for all C chemicals, we need to subtract C times P minus 1 from this expression. So again, we have this expression. This 2 denotes pressure and temperature. And then we need to subtract this C times P minus 1. These are the number of equations for chemical potentials. And then we have P times C minus P plus 2 minus C times P plus C. The result is C plus 2 minus P. In conclusion, we have C plus 2 minus P, independent variables that may vary freely. And therefore, we say the number of degrees of freedom is C plus 2 minus P. For example, if there's only one chemical in the system, then F equals 1 plus 2 minus P equals 3 minus P. The triple point has only 0 degrees of freedom because P equals 3. 3 phases coexist at the triple point. The coexistence lines between two phases have only 1 degree of freedom. Again, we plug in P equals 2, and then F equals 3 minus 2 equals 1. There's only 1 degree of freedom, or we can say there's only 1 independent variable that may vary freely. When there's only one phase, both pressure and temperature may vary freely. Therefore, the degree of freedom is 2. We can also plug in P equals 1 here. F equals 3 minus 1 equals 2. This derivation is not included in the Engel and Reed textbook or many other textbooks. And it's not exact, but at least I think it provides you some basic understanding of the phase rule.